G'day, in this video we're going to start looking at the Bohr model of the atom. This video focuses on dot points 8.3.1, 2 and 3. It's a verse video that covers content in inquiry question 3, which reads, how is it known that classical physics cannot explain the properties of the atom? In summary, these dot points account for the history in the development of our understanding of the atom, but particularly the properties and behavior of electrons. We've already begun to address dot point 1 in previous videos, where we looked at the limitations of the Rutherford or planetary model of the atom. Today, we're going to expand our understanding by looking at the Bohr atomic model and how it built on the planetary model that already existed. However, the Bohr model comes with its own flaws too, and we'll be unpacking that towards the end. The Bohr model is particularly effective at explaining observations that we see in spectroscopy, and as such, we're going to be linking concepts of spectroscopy to the Bohr model of the atom itself, both from a conceptual and a quantitative perspective. Our key learning intentions for today are to first understand many of the scientific principles which were available to Bohr in his time. This includes the Rutherford model of the atom, as well as other concepts which Bohr was able to explain using his updated atomic model. One of those key concepts is going to be centered around spectroscopy. And so we're going to investigate the spectra of hydrogen and the quantitative relationships described by the Rydberg equation. Once we have an understanding of all of that, that will then allow us to understand Bohr's actual model. We'll then talk about the contributions made by the work and, as always, limitations of the model as well. Concepts which underpin Bohr's model first start in the days of Isaac Newton, who, when observing the dispersion of light from white light to all of its parts in the visible spectrum, Newton, who believed light came in the form of particles, which he named corpuscles, suggested that the light bent through his glass prism by differing amounts due to the differences in size and mass of the particles. While we know this to be untrue, this observation was the first step into understanding the spectra of light and the beginnings of spectroscopy itself. In the early 1800s, some physicists of the day were very focused on observing the spectra that they found from stars, particularly the sun. William Wollaston was the first person to, at the very least, record, if not observe, the dark lines in the spectra of stars. His explanation of what he saw was quite simple and straightforward. He was of the opinion that these were simply gaps between the colours which were emitted by the sun. We now know today what's actually happening is that light in the atmosphere of the sun is being absorbed by the matter that is there. And thus we see these dark bands of spectral lines which show an absorption spectra. These are concepts that we did break down at the beginning of Module 7. Joseph von Fraunhofer continued this work, and he was able to identify 15 separate, unique dark lines from the spectra of the sun, and these are now referred to as Fraunhofer lines. However, we do know that there are about 25,000 Fraunhofer lines which exist in the spectrum of our sun. And while Fraunhofer was making these observations, he didn't have a complete understanding of what was happening and why. At this time, we knew that the spectral lines existed, but not their cause. As we progress into the mid-1800s, we start to get a little bit of a clearer understanding of spectra. Gustav Kirchhoff and Robert Bunsen were a pair who were quite prevalent in the field of spectrometry and completed a lot of experiments together. Their particular focus was with discharge tubes, which we've looked at before in class. By placing a high voltage between specific gases, you are able to make that gas light up with specific colours. The spectra of these discharge tubes are unique and are essentially a fingerprint which can be used to identify the gas present inside the tube. By identifying the spectral lines of sodium in particular, they were able to see within the spectrum of the sun that sodium was an element present within the sun. They were also able to identify cesium and rubidium by their spectra. Essentially, these spectra of unknown materials which they were able to produce did not match up with the spectra of any other known substance. As such, they realized that they had produced a new substance. This method was quite unique and had not been used previously to identify an undiscovered substance. Through this work, Kirchhoff also developed the 3 laws of spectroscopy, and they were as follows. Hot dense materials emit light of all wavelengths, creating a continuous spectrum of light. This can be seen in the leftmost part of the diagram, and it's this concept which essentially is outlined in Wien's law, but is essentially a mathematical relationship of Kirchhoff's first law of spectroscopy. The second law states that a hot, low-density gas emits light at a specific discrete wavelength, resulting in bright emission lines. That is the right part of this diagram. In other words, if you are able to provide a gas cloud with energy, it may begin to glow, similar to a discharge tube. And those emission lines, like we said before, form a fingerprint which is indicative of the particular material that it is composed of. And the final rule, which we can see in the middle, if you have a continuous spectrum passing through a cool, low-density gas, then the gas will absorb certain wavelengths of light, which we see as absorption lines. And that these wavelengths for absorption correspond with the wavelengths of emission for the emission spectra of the gas. What this thus implies is that the black dark lines, the Fraunhofer lines that we see in the spectra of the sun, are actually caused by the absorption of light by the atmosphere of the sun as the light itself escapes the sun and heads towards the earth. In the mid to late 1800s, there was a lot of experimentation going on with spectroscopy and discharge tubes. But Johann Balmer, who was by trade a mathematician, also began to dip into this field as well. And his goal was to try and find a mathematical relationship which could relate all of the wavelengths of the visible emission lines of hydrogen. And he came up with this formula here, that lambda is equal to B multiplied by m squared divided by m squared minus n squared, where lambda is the emitted wavelength that's in the spectra, B is the Balmer constant, which actually makes this formula work, and m and n are both integers, where m is always greater than 2 and n is equal to 2. What this means is, if Balmer was to sub in B and M, which are effectively both constants, and put in any value for M that was greater than 2, he was able to calculate for the wavelengths that corresponded with the emission lines in hydrogen. In essence, he was able to develop an equation which fit the experimental observations at the time. Do note that we don't actually use this formula within the course, but it is the precursor equation to the Rydberg equation, which we'll have a look at momentarily, which is something that is in our data sheet and is something that you are expected to calculate with. So fittingly, in comes Rydberg a few years later. He was developing his own formula to relate the wavelengths of all of the lines that can be found in a spectra. Once Balmer's equation was published, it actually provided a point of inspiration for him to develop and refine his own formula that he was already working on. And this is the one here. This shows up in your data sheet and is one that we will learn to use. Again, lambda is the emitted wavelength. R is the Rydberg constant, which is different from the Balmer constant. And F and Ni are integer values. In some formula, you may see them referred to N1 and N2 respectively. It should also be noted that Nf, the first fraction in the equation, should always be lower than Ni. And therefore, Ni should always be larger than Nf. Functionally, what this means is that the denominator of the first fraction will always have a lower value than the denominator of the second fraction, meaning that when you substitute the two fractions from each other, you always end up with a positive number. Again, this formula was empirical, meaning that it was created by making the equation fit the already observed and measured wavelengths of the spectral lines of the hydrogen spectra. What was advantageous about this equation as well was that you were able to predict for other wavelengths in the hydrogen spectrum that weren't just observed in the visible spectrum. Essentially, the difference between the two equations comes down to the fact the Balmer formula always had a value of n equals 2, and in the Rydberg formula, Nf can take any value, not just 2. That will make a little bit more sense when we start to unpack what this means quantitatively in terms of electrons. We should also note that the Rydberg formula only works for hydrogen, and quantifying the wavelengths of spectral lines for other elements with more than one electron is significantly more complex. So in Balmer's time, he had a lot of information and scientific understanding around the concepts of spectroscopy. But only a decade before were the foundations and the beginnings of our understanding of quantized energy and the beginnings of quantum physics. In Module 7, we looked at the idea of the ultraviolet catastrophe. To summarize in short, classical physics suggested that hot objects should radiate large amounts of higher and higher frequency radiation. But when we look at things like stars, which we knew were to be exceptionally hot, they didn't follow this pattern when we looked at their spectra. There was a big dip after the visible spectrum. Planck suggested that for large amounts of energy to be emitted from a high energy particle, it would mean that all of that energy would have to be emitted all at once. This concept and his mathematics helped to support the idea that electromagnetic radiation actually came in packets or chunks of energy that he referred to as quanta. And the idea of light energy existing in quantized photons was experimentally proven when the photoelectric effect was demonstrated and explained. The results of these experiments showed that the number of electrons which were produced depended on the number of photons incident to the metal. And as such, the energy of the light itself that was being shone on the metal had no impact on the photocurrent or the number of electrons being dislodged. Instead, the intensity, which dictated the number of light packets which struck the metal, dictated the photocurrent. Essentially, more photons meant more interactions with electrons. More interactions one-to-one with electrons and photons led to more electrons being dislodged and therefore a higher photocurrent. So Bohr had a lot to go on when developing his model of the atom and improving on what Rutherford already had. He had Rutherford's planetary model, the understanding that there was a centralized nucleus of positive mass and surrounding electrons. We also had an understanding of spectroscopy in the Rydberg equation and Planck's concepts of quantized energy. Bohr's initial model of the atom did not include protons and neutrons, as these were yet to be discovered. This was an element of Rutherford's planetary model, which he wasn't able to address. Instead, his model improves our understanding of the nature and behavior of electrons, which can be explained by spectroscopy, the Rydberg equation, and Planck's concepts of quantized energy. So in order to enhance this model, Bohr developed a series of postulates to combine all of these concepts together. The first being that electrons orbit the nucleus due to Coulomb forces. This was still the same as a Rutherford model. There were no improvements, even though scientists of the day understood that this was not an ideal or perfect explanation. Where his model differed from Rutherford was the idea that the angular momentum of the electrons in orbit were quantized. Effectively, he was trying to bring quantum physics into our understanding of the atom itself. And because there was a quantized amount of angular momentum that these electrons had, there were only specific orbits that the electrons could exist in with set or quantized radii. In other words, the electron could exist in one orbital or another orbital, but not in between. He suggested that at these particular orbits, they existed in stationary states. What he suggested was that in these stationary states, the energy of the electrons was stable and constant. In other words, they were able to orbit around the nucleus without having any energy changes which would lead to the emission of radiation. Effectively, this concept explained or accounted for the idea that an atom at rest also had electrons that weren't continuously changing their energy levels. And really, this postulate existed to account for the limitations of considering electrons being something that orbited classically. Beyond this, though, electrons under special circumstances would be able to change the orbits or the shells that they existed in. And this could be done by increasing or decreasing the amount of energy that the electrons had. Electrons could radiate energy. In other words, they could release energy. And that would mean that they would transition from a higher orbital associated with a higher energy level to a lower orbital associated with a lower energy level. But the electrons at the lower orbitals could also absorb external radiation, meaning that there would be a gain in energy and a transition from a low energy orbital to a high energy orbital. So effectively what was happening here is that the energy which was being absorbed or radiated was always equal to the differences in the energy levels between the orbitals. If we were to use simple numbers here, let's say that the first orbital here meant that the electrons had 10 joules of energy, and this orbital here meant the electrons had 30 joules of energy. If there was a transition between the two orbitals, the electron would either be gaining or losing 20 joules of energy in order to do so. And this energy that was either gained or lost was gained or lost as a photon or a packet of light. Either a photon of electromagnetic radiation externally came in and was absorbed by the electron, or the electron dropped and released a photon of light with equivalent energy. These postulates quite closely relate to what we observe with absorption and emission spectra. The release of light from electrons in an atom are due to the atom returning from a high energy level to a lower energy level. And absorption spectra is caused by electrons in low orbitals absorbing energy of set wavelengths and therefore set energies as they ascend to a higher energy level. This is quite nicely shown here in the diagram to the right. When the electrons jump to higher orbitals, they need to absorb more energy, and thus the wavelength of this energy is shorter, the frequency is therefore higher, and therefore as well the energy of light being absorbed is higher also. Bohr's postulates also explain why for a particular element, absorption lines and emission lines perfectly line up. In terms of this red line here that is a characteristic 656 nanometers, it represents a transition from n equals 3 to n equals 2, or energy level 2 to energy level 3. When there is absorption, we're going from 2 to 3, and when there's emission, we're going from 3 to 2. The Rydberg equation does a fantastic job of modeling the Bohr. The Rydberg equation does a fantastic job of quantifying the things predicted by the Bohr model of the atom. These n values correspond directly with the orbitals that are found in the hydrogen atom. As such, when we calculate for a transition from a higher orbital to a lower orbital, we can calculate for the wavelength and therefore the corresponding energy of the packet of light that is emitted, the photon that's emitted. Let's do a quick example. In this example, I'm going to calculate the wavelength of light which is emitted when an electron in a hydrogen atom transfers from orbital 3 to orbital 2. Note that because we're transitioning from 3 to 2, the initial orbital is equal to 3 and the final orbital is equal to 2. As stated earlier, the first fraction with nf should always have a value higher than the second fraction with ni. This will always mean that the two fractions inside the brackets yield a positive number. And this is important because you can't have a negative wavelength. We should get the number 1.52 times 10 to the 6, except this is the reciprocal of the wavelength. As such, we'll need to take the reciprocal of the right-hand side to calculate for lambda. And we should get 656 times 10 to the negative 9 meters, or 656 nanometers. This is the characteristic red line that we just looked at in the previous slide. And as shown in the diagram here, is the wavelength of light which is emitted when we're transitioning from n equals 3 to n equals 2. We should note also that there are 3 characteristic series, and that each series corresponds to the descent from a higher orbital to the same final orbital. The Lyman series shows transitions that end up at n equals 1. The Balmer series are transitions that go to n equals 2, and the Paschen series highlight transitions that go to n equals 3. In the Lyman series, we have short wavelengths that correspond to UV light. The Balmer series corresponds to wavelengths associated with the visible spectrum, and the Paschen series have long wavelengths which are associated with infrared light. So what did this model actually do? Well, the Bohr model explained observations made through decades of work in the field of spectroscopy and deepened our understanding of the behavior of the electron. It didn't really solve a lot of the problems of the Rutherford model, but it certainly connected our understanding of the electron and its behavior to other phenomena that were also observed, and connected our understanding of matter at the very smallest scale to what we observe with light and energy. What's also particularly consequential about this work was that for the first time, the concept of quantization was being introduced to our atomic model. Bohr's model is a little bit funky though, because it still has a bit of classical physics in there and they don't really like to exist in the same space. But this was certainly a stepping stone that helped us to transition away from explaining atomic physics using our classical principles. For the rest of this inquiry question, we will transfer away from classical physics when understanding the electron. As alluded to already, there were some pretty big limitations with this model. The biggest being that the model combined classical and quantum physics, and they do contradict each other. We were still using this idea that orbits and circular motion were the reason why the electron doesn't just collapse into the nucleus. Bohr did try to explain why an orbiting electron wouldn't just lose energy and collapse into the nucleus, and his idea that electrons sitting in stable orbits not radiating was a sound one to explain what was experimentally observed. However, this was completely at odds with fundamental understandings of electromagnetism. And therefore, if this assumption was true, it did violate the current understanding of the day. Similar to Rutherford's concepts, we were able to improve our explanation and build on atomic theory, but ultimately this was just a convenient explanation that was the best explanation that we had. Scientists of the day knew it was imperfect, but it was better than the explanations that existed previously. Another big limitation in this model was that it only applied to hydrogen. And this was because the Bohr model in part was based on the Rydberg equation. And at this stage, this was the only mathematical formula or equation that could be used to predict electron behavior as it transitioned from one orbital to another. Further to this, while Bohr was able to take concepts of spectroscopy and explain them using his atomic model, there were some phenomena that were known about the spectroscopy of different substances which Bohr was unable to explain. Spectral lines have differences in their intensity. We can see that in our hydrogen spectrum here. The red is by far the most intense, and in this picture, the purple are near invisible. Bohr had no great explanation to account for this phenomena. Furthermore, if you were to take high resolution spectra, you would find that individual lines were actually broken up themselves, and there were several hyperfine lines which, when combined together, made a much brighter line. This again was unexplainable by Bohr. Scientists at the time also knew that if you were splitting light into spectral lines, but place that spectra in the presence of a magnetic field, the Zeeman effect started to arise. And similarly, in the presence of an electric field, the Stark effect arose as well. And what you would see instead of one spectral line was a splitting pattern occur instead. Again, Bohr could not account for this or any of the others. This brings us to the end of this video, and in our next video, we'll continue to develop our understanding of the electron and its behavior. Particularly, we're going to be looking at the particle wave nature of matter. Previously, we've looked at how light has a particle wave duality. Turns out matter does as well, and it is quite a brain bender. But that obviously will be the subject of our next video. So until then, have a good one.